movies. Are they good movies?
Oh, that's
Yeah.
true.
Okay. Well, in my opinion, they are. But
Yeah, they are good movies.
to other people, maybe not 3 of them. But I watched the first Hobbit movie last night. Took 4.5 hours to get through it, and I took.
Oh, you watch like the extended cuts and stuff.
And that was the normal one.
Oh, because you're stopping and making notes. Oh.
I did 7.5 pages of single space notes.
Single?
Just,
Okay.
Basement.
yeah.
Oh, my
Okay.
Obviously,
Lord.
not all of it is gonna make it into what I'm talking about, but I was like, I need to cover all my bases just in case I need to go back and find something or whatever. So it's kind of.
It is. Bless you.
Sorry, thank you.
It's all right. You're having fun. If you didn't want to do it, you wouldn't do it.
I know.
You're making you do it.
I know.
That's my favorite thing to do. I
Make
don't want
yourself-
to do it, so I'm not going to do it.
There you go. She wants to do it.
I'm proud of you. I don't have a whole lot of self-control. And just
Yeah, you do. You're working. You're going to school. You're trying. You're doing your damnedest. And all right, friends. So, does anybody have any questions on that homework assignment?
Oh boy, do I.
Great. And if there's stuff that we need to like put off, because we'll talk about it today, that might answer it, I'll let you know. But what would you like to start with, my friend?
Can we start with number 1? And it's mostly just the creating the, what is it, like the first one, like step number 1, creating the.
Create the bijection.
Yeah.
Okay.
Like I can prove that something's 1-to-1 and
I think you're making this much harder. So let's
Yeah,
see.
probably.
Let's find an isomorphism between the group of integers C.
Oh, hold on, wait, I lied, number 4.
Okay, I was like,
I was like,
this one's
Wait,
not that
yeah,
hard. We
sorry.
did this kind of
did I
question.
write it down wrong? Or did
No,
I-
no, no, it's cool. Good. It's good. Yay, you made it. All right, outstanding. Number 4 was the actual number?
Yeah.
Okay. Oh, okay. We are going to address this today, but maybe I'll use it as like kind of a segue. So show U8 is not isomorphic to U10, but that it is isomorphic to U12. So maybe it's as good a place as any to start. Yeah. So we're going to have to actually pop a couple results out to get this done. And we didn't get to them, so that's probably part of why it's kind of like, I don't even know where to go with this. But let's check out theorem 6.1 together, and let's see what page is that on. Because that's our key to at least the first part, and then we'll talk about the second part. Where the hell is theorem 6.1? Yeah. So, theorem 6.1's got a lot in it. Let's just go through it because I wanted to read through it together. We're on when you get there. When you get there, oh yeah, that's going to be page 131. You okay?
Oh, it's just been another stupid morning. Oh gosh.
Well, you're here now. Everything's better.
We're proud of you.
Yeah, absolutely. Okay, so page 131. So phi is an isomorphism from a group G to a group G bar. And so it takes the identity to the identity. That's super essential. That's actually really key in building isomorphisms sometimes, and we're going to use that today. Let's kind of skip through. So like there's some little intermediate results in there. 3 is really important because it says that if A and B commute in the group G, and G is isomorphic to G bar, then the images of those also commute. So one key thing there is if 2 groups are isomorphic and one is abelian, the other must be abelian. So that's kind of a way to show 2 things aren't isomorphic sometimes. So I've got this one thing and everything commutes. I got something over here and not everything commutes. They can't be isomorphic. So that's how that would get played. If G is cyclic and isomorphic to G bar, then G bar is cyclic. That's number 4. So if one's cyclic, the other's cyclic. Then check out number 7. If G is finite and G, and that should say and G bar, does yours say G and G? Yeah, good and good. If G and G bar have exactly the same number of elements of every order, and that's what we're going to look at here. So if two things are isomorphic, and one's got 7 elements of order 2, the other one has to have 7 elements of order 2. They have to pair up that way. And if those don't match up, then they're not isomorphic. That's how you can really bust two groups into not being isomorphic. So let's check out number 4 here. It says show U8 is not isomorphic to U10. And like on more basic level, they have to have the same size, right? So if they don't have the same size, they can't possibly be isomorphic. So let's first write out U8. And so that's 1, 3, 5, 7. And then U10 is 1, 3, 4, 7, 9. Yeah. Cool. So they have the same order as the group. The groups have the same order, so that's not going to destroy this at all. But let's start checking out the orders of the elements. Okay. So what is in this group here, the identity is 1. We don't need to really address that. What's the order of 3 in this one? So 3, remember multiplication in these U groups. So it's mult, mod, 8. So 3 squared is what? 9, and then 9 mod 8? 1. So what's the order of 3? Good warm up for the day. 2. Beautiful. What's the order of 5? Now that we're warmed up on playing that game. 2 again, because you get 25. Mod 8 gives me 1, so order of 5 is 2, and what's the order of 7? It's also 2. And then we also have, you always have the identity, so the order of 1 is just 1. That's not super enlightening. So down here, we've got the order of 1 is 1. What's the order of 3 down here? And as soon as we know it's not 2, it's not 2, right? It's more than 2, because 3 squared is 9, and that's not the identity. 3 cubed is 27, and 3 to the 4th gets us back to the identity. So in fact, 3 is a generator of that group. Yeah. So here the order of 3 is 4, and this doesn't have any elements of order 4, so they can't be isomorphic.
Okay.
You see how that works?
Yeah, that was a lot simpler than probably just
Cool. Alrighty, so let's see, and then part 2 was to show that U8 is, though, isomorphic to U12, so I guess we really need a U12 out here. So U12 is going to be 1, 5, 11. And let's just go through, let's see, what's the way to proceed here? Well, we know that 3 is a generator of this group. So first up, I'm just going to kind of write this down. We know 3. Is 7 also a generator of this group? Yeah. Yeah. I think they're all generators. Because 9, oh, no, 9 has, is that right? Yeah. Mm-hmm. Yeah. So, but it doesn't equal, so that's equal to those. So the order of 7 is also 4, and the order of 9 is just 2, right? Yeah. Go. Okay, so we want to create a mapping feed. I'm going to put U10 just right up here, so we can just have it of So one of the things that's gonna help us here is, first off, we know that phi of 1 from U10, so we're gonna make a phi that goes from U10 to U12. What happens, what does this have to be, given theorem 6.1? 1 has to be 1. Identity always goes to identity, so theorem 6.1, part A, E maps to E under your isomorphism. And this might be a different identity, but
Are we doing U18, 12?
I'm sorry, what? Oh yeah, what am I doing here? Oh no, yeah, we're doing, 8 and 12, not 10 and 12. Thank you. Thank you, Pam. Good call. So that's actually 1, 3, 4, 7. There we go. This still holds for us, so we got that going. So now we just kind of have to figure out how to map what to what, and give it a shot and see if it works out. We have to make sure that we have a bijection. We have to make sure that we preserve the group ops. So let's take a look at element or result 4. So theorem 6.1, part 4. I'm going to write that up here because it's going to help us. 6.1, 4 says that G is cyclic, or G is cyclic if and only if G bar is cyclic. And that the image of A under the isomorphism actually still is a generator. So let me write this in like some language here that is like a sentence. If A generates G, then phi of A generates G bar. So we know we have a generator of U10, and that's at 3 or 7. Do we have a generator of U12? So we probably need to do a little bit work with U12 just to kind of think this through. So the order of 1 is 1, the order of 5 is what? 2. Order of 7? Huh, wait, so
Because we're comparing U8.
oh, we're doing U8, thank you. Oh, Jesus, okay. Okay, yeah, it's getting really, really somewhat terrified there. Did I not change this? Oh, I just didn't rewrite my notation, did I? Okay, there we go. Whew, okay, so let's get rid of this. Let's get rid of this. Okay, so everybody has, so yeah, this might not be the thing that I'm thinking of then, because the order of 11 is 2. So we don't have the cyclic groups in this case. I was thinking we were working with the other one, the U10, which is cyclic, but this one's not cyclic. But you can see that it lines up with the element orders here. So we do need theorem 6.1 again, because we know that the order has to be preserved under the isomorphism. So yeah, so part 5, theorem 6.1 part 5 says order is preserved. So let's actually put that up here. Phi preserves element order. So at this point, I kind of just need to make a stab in the dark. I've got these elements of U8, which are 1, 3, 5, and 7. And I've got these elements of U12, which are 1, 5, 7, and 11. This has to go to this. That's done. But I've got 3 elements of order 2 here and 3 elements of order 2 here, and I'm just gonna make a call. And then we're gonna see what happens. So, let's suppose that phi of 3 is equal to 5. That preserves order, so we're all good. Let's see, then we know 3 squared is that. Yeah, I think we might have to just kind of make a stab in the dark and let's try it. Let's just try phi of 5 is 7 and phi of 7 is 11. Just see what happens. This is so small that it's okay, you know, to just give it a shot. And if we screw up, we'll just tweak some things here. Is this making sense from what I'm doing, Kyle? Yeah? Explain what you're. You have an interesting look on your face. I'm trying to read it.
That feels like we're just. It doesn't matter. Like they're all ordered too.
Yeah, it may or may not. It probably doesn't here, and because we might actually have. Let's see how many different ways are there to assign. We might have 6 different isomorphisms, because this first one could go to any of those 3, and then the last 2. So it's a counting problem at that point. Well, let's just. Let's try this out and see what happens. And here's a great way to see if this is true or not. Let's look at their Cayley tables. So let's do the U8 table. 1, 3, 5, 7. So that's 1. And then let's do the Cayley table for U12 over here and see if we can just swap these elements here and have the tables look the same. Because that's essentially what an isomorphism is. We're just changing symbols. One. Oh yeah, these are all ones, right? Nice ones down the diagonal. What's 3 times 5? 7. And then this must be 5. 7. Because this is all commutative too, so that's nice. That's symmetry. 35. 3? Yeah, gotta be 3. Yeah. Okay, so this table here then is going to be 1, 5, 7, 11, 1, 5, 7, 11. 1, 1, 1. And then what's it's 35 is 11, 11, 11. And then this must be the 7, 7, 5. So I think this actually demonstrates it quite well. That if I take everything here and I make that replacement scheme, so I replace every 3 with 5, I replace every 5 with a 7, and every 7 with 11, I get the exact same table. Do you see that? Is that, yeah. So I would just make some notes here that, and you can define your phi like this. So let's define phi like that. It's a little sloppy here, or you could do it like this. That's also great. And note that if we replace elements of the U8 table with the scheme, we get the U12 table. So with these smaller groups, you got 4 or 5 elements, you can be very explicit about what's going on. And I kind of think, as you were suggesting, Kyle, I kind of think we could do this in 6 different ways. So I think if 3 went to 7, that would also work. It's not quite as obvious that it would work, but I feel like there's 5 more answers here. We only need 1. To show there's an isomorphism, we just need 1 of these. Does that feel good? Yeah? What else do you want to talk about? I don't quite even remember what the other problems were.
Number 3 has to do with automorphism.
Right. So let's talk about that, because that was kind of on the agenda for today. So yeah, let's get there. And when was this supposed to be due? Like Wednesday?
Yeah.
Okay. Let's see what we get through today and see how you feel about that as being our due date still. But wanted to warm up with some things we have U10 up already, so that's very handy. Show that U10 is isomorphic to C4. So let me give you some hints on this. U10 was nice and, well, actually, I'm gonna let you think about it for just a minute, because I have to run to the restroom. That provides me an excellent opportunity to do so. So see what you can do here. Think about identities have to map to identities, orders have to be preserved, generators have to be preserved. I'll be right back, just give that some deep thought. You can kind of, there's a high level argument possible here. If you note something about their structures, then you can kind of just note that and you're done. What was that problem you were asking about actually, Sydney? Oh, it was 3 with the inner, okay. Yeah, got it. Anybody getting any hints about how to proceed, maybe? has to be true about that. Bless you.
Zero.
Has to be 0, yep. Identity plus you again. Identity has to go to identity. I think we showed every element's a generator of this group, right? We talked about that, because 3, 9 isn't, that's right, but 3 and 7 were, yes, thanks, Kyle, yeah. But I could write this whole group like this. Let me see if this helps. 3 to the 0 is that, 3 to the first is that, 3 squared, that's not, oh wait, that's this guy here, right? And then this is 3 cubed.
Yep.
Cool. Does that make any suggestions to us about what we might want to try? Yeah, it's a pretty strong suggestion, right? Because you can look at those exponents there. So let's give it a shot. Let's just try this. Phi of 1, 0, phi of 3 is 1, phi of 7 is 3, and then phi of 9 is 2. So one thing's pretty obvious, that's a bijection, and it's on 2. So we don't have to, you can look at that. Does that make sense what I'm saying there? Each element here gets sent to, each element over here corresponds to exactly one element over here, and I hit everything. So this is 1 to 1 and on 2. So really all I have to do is verify that it preserves group operations for me. Did anybody go this route? Or Kyle, you were right a lot. I saw you.
Yeah, I just kind of, I don't know, guessed and checked it. In the sense of, I knew 9 had to go to 2, and I knew 1 had to go to 0, so I started with phi of 3 goes to 1.
And then
phi of
just
7.
started experimenting.
Yeah.
Yeah. How can we verify that this has preserved the structure? Tips. Cayley table. Like when things are this small, do a Cayley table. So let's do the U10 table. U10 table, which we've probably already written up a couple of times. Must be 7. Must be, this is commutative, so that must be 1. This must be 7. Let's see what goes here. 7, 7, 9. 3. I think that looks good. Take your word for it that I did that right. And now let's look at the Z4 table. Say that again, Kyle.
Do it 0, 1, 3, 2.
Yeah, exactly. So that we've got the order lined up so we can actually see the pattern aligned. Because these are just ordered because that's what our brains do because we're humans. But they don't have to be in any order. You pick that order. So 2, 0, 3, 0. And you can see the rhythms starting to play out quite well here. This is the 9 and the 2. Everything's looking really beautiful. 2, 0. You can see that if you make those substitutions into that table, you get that table exactly. Take a look, make sure you see that. This is plus. This is times 4. You see what's up with that, Sydney? Is that making sense? Yeah. Trinity, you good on that work? Okay. So here's another puzzle. R So here's kind of a more, yeah, let's just ask these in a more general way than I was going to. Is D3 isomorphic to Z6? Oh, yeah.
Like those dihedrals, when you see those, you're like, oh shit.
So first thing to do is note that they both have order 6. So that isn't going to bust it. Check the orders of the elements. And you should understand D3, I think, well enough. That's not too bad, right? It's just the rotations and flips of a triangle, equilateral triangle. So examine orders. There's a couple things you can, a couple quick things you can find that'll answer this question for you. We don't, thank you. Glad to have you here, keeping an eye on me. Thank you. A little excited. There's a couple of ways to approach this. You could definitely use theorem 6.1. One of the first 4 parts. Help. There's a lot of ways to do this. Worked out some more, Kyle.
Yeah?
Yeah, I did. Yeah, been drinking pre-workout and shit like that, taking
Never
creatine. Yeah, you probably don't need to. Yeah, yeah. I know my legs are killing me this morning.
It's good. It's a great feeling.
It is. It's fantastic. Yeah, it's really helped with my energy.
Yeah.
Definitely. Yeah, we did lower body yesterday, so I really can barely walk. But
I mean, if you
it's a
haven't
good
lifted
feeling.
legs in a while and then you do legs, your legs are sore for a week.
Yeah, but so you don't do any like nutritional stuff like before you work out or like
Nothing crazy. I put as little into my body that is supposed to affect things as I can. So I don't try to do as little caffeine as I can. I don't take any. I don't.
Let's grab our caffeine.
Mine's water.
Oh wow.
I have water.
I don't. Yeah, I don't take medicine unless I'm dying. For the most part, I try to keep everything
That's cool.
as natural
Yeah.
as humanly possible.
Nice. Yeah, we were taking like these, like the creatine, and then there's another protein thing we're taking. I mean, we're vegan, so we like to add like some extra
Protein
protein.
powder. I do protein powder.
Yeah, it's something equivalent to that. I forget what kind of protein it is. But I don't. You seem like you have an answer on this one, Kyle.
I do. I think. One is a generator of Z6. There's no generator of T3.
Beautiful way. Knock that out. That was a one-liner. Yeah. So this group is cyclic,
Yeah.
right? This group is not cyclic. So that's beautiful. So let's do some arguments. Z6 is cyclic. D3 is is not. That's a great argument. If you didn't see that, that's okay. What are some other ways to see that these can't be the same? That's beauty. Anybody else look at anything else? Sydney, what were you checking out? You were checking out? Trinity, did you come up with any strategy here? Okay, let's go through that. Let's do the orders. So up here we'll have the orders. This is order 1. This is order what? 3. This is order 3. 2. 2. And then over here, 1. Kyle, as Kyle said, that's 6.
3, 2, 12, 3.
Because it's the inverse of
Yeah.
2, right? So they have the same order.
Yeah.
And then 6. So 2 elements of order 6, 2 elements in order 3, and 1 of 2. Not that there. So that's another argument. So that's 1 or 2, compare orders. Good stuff. Here's another one. Is U6 isomorphic to Z6? We'll be able to answer this. This might be the fastest one of all. So is U6 isomorphic to Z6? That's a good answer. Just give me a Y. Yeah. Is that what we all see in that? Like, U6 is pretty dang tiny. How, so, what is U6 isomorphic to?
That's a different question.
Yeah, it is. So this is a little more open question. So we can see that this isn't isomorphic to U6. Trinity, are you cool with that? Yeah. U6 is just 1 and 5. Not isomorphic to Z6 because there's 6 things here. So no, not the same number of elements. Seems like a thing to try, doesn't it? Let's check it out. But so is U6 isomorphic to Z2? And what do we have to do? We have to produce an isomorphism. It's not, there's not a lot of options. Because in U6 we've got 1 and 5, Z2 we've got 1 and 0. And this has to be, and then this must be.
Yeah.
And over here 5 squared gets me 1. And over here 1 squared is 1 plus 1 gets me 0. So I would set this up as my phi of 1 equals 0, phi of 5 equals 1. And you pop out some Cayley tables if you want. Show that these tables are identical. I mean, they're really beautifully identical, actually.
My favorite kind of tables.
Yeah, right. Oh, whoa, easy boy. Easy big boy. All right, there we go. Isn't that crazy? Yeah. Pretty, very nice and simple. We gotta be happy with that. All right, let's talk, one more example. I wanna show you one more example. Because it'll kind of help with our problem 3 that Sydney was asking about. So, I better grab this out of here. Let's say we have phi, theoretically an isomorphism from R under addition to R under addition. Can you think of one of those off the top of your head? Can you give me a phi just like that would work? Something we could try anyway. Just has to preserve addition, be 1 to 1 and on to. Don't get too crazy. It's like the simplest functions in the world.
pretty bad one. It's pretty uninteresting. Works. This is actually, well, I won't say it. What else could I try maybe? Will this work? Let's take a look here real quick. So here's R. Here's x cubed. And so here's R. That's 1-to-1 and onto. 1-to-1 passes the horizontal line test, so it's 1-to-1. It's onto because it's working onto, right? So this is 1-to-1 and onto from R to R. Is it an isomorphism under addition? So what do we have to check? What do I need to check here? Does it preserve group op? That's the question. So here's the two things being added here. You tell me, does it? Remember, here's what we're asking in case you're not quite sure. Is this the case? Sometimes it depends on who you ask, if that's true or not. I hope we all know the right answer. Yeah, that's a good instinct. So what does this side look like?
First part.
Yes.
Yeah. and
That?
then-
Yeah. And then what's this over here?
B of x cubed 1 or x cubed plus y cubed.
Yeah. Is that true? Thank you so much for saying it's not true. I still have like people in 400 level math classes sometimes making that mistake. That's like called the freshman's dream. That this can happen. If we have multiplication, sure can. That is not true. That is a lie. So it does not. This is not an isomorphism. Because it doesn't preserve the group operation. But what could we maybe try? So phi of x plus y, when would that be the case? Have you had linear algebra?
Heck yeah.
So long ago. So long ago. So long ago. Doesn't this look like linearity, part of linearity?
Sure.
What's the other part of linearity?
Wonderful question.
So this is part of linearity. This would say phi is linear, almost. Then what's the other one? We have like an alpha. What can you do with that?
Let's get out the alpha.
Bring it up, right? So that's linearity. We don't really need that second one. We need just this part of linearity. So I'm saying a word here. A linear function. Give me one.
2x.
Let's try that. Yeah. Okay. So that's 1-to-1 and onto. I'll allow you to verify that on your own time. It looks like this. well, more or less. Roughly, yeah. Roughly. So it's 1-to-1 and onto. You could easily prove that with the definitions, not hard at all. Does it preserve group op?
So that'd be
Yeah, what's the left side gonna be? What's this?
2x plus 2y.
Yeah, so that's that, right?
Or, yeah.
Yeah, and then using just properties of distribution. Got it. So that is an isomorphism. So this, give me a whole class of isomorphisms.
All the
Anything as long as it's not 0, right? Which would kill everything. If I put 0 there, it just crushes everything to a single number. That doesn't sound very onto-ish. We're trying to be onto-ish. And Yeah, what if I put a constant on there? Does that still work? A non-zero beta? No, let's try, right? Let's see. If we did that, that's still 1-to-1 and onto, provided alpha's not 0. Just shifts this up a little bit. Ooh. Is this true? Beta is not 0. So yeah, what's over here? Say that again. Sorry. If we're just using this general form with that alpha, and that beta, what's phi of x plus y? Don't think too hard.
X plus y plus b.
Yeah. Is that going to be the same on the right side? So what's over here? We've got alpha.
Alpha y plus beta.
What has to be true for those to be equal?
Yes.
Beta has to equal 0.
So for these to equal, only if.
Cool. Little warm-up discussion. Little warm-up discussion for about an hour. This is an example of an isomorphism of a group back onto the group. That's called an automorphism. So that's the definition of automorphism that you need for that problem 3. And probably knowing that, you could proceed with it, but let's just get really quick definition. And automorphism on a group G, so it's only on a single group, is an isomorphism of G onto itself. So when you look at problem 3, then Sydney,
It gives you the fee, right?
yeah, and they give us the phi there, so really it's just another, is this an isomorphism of R plus onto R plus? And under multiplication, yes, which would be really essential, because certainly, this is also a freshman dream, but that is true. It's not true, right? But with times, everything's all hunky-dory, whatever that means. So, let's talk about some super meta things. Things are gonna start lifting off into the stratosphere a little bit in our class.
So define, so G is a group. Define ought G, so it's AUT of G,
To be the collection of all automorphisms of G back onto itself. Equals the collection of all phi, such that phi is an isomorphism of G onto G. So the things in here are functions. These are mappings. So just keep a note that the elements are bijections of G onto G that preserve group order, preserve group structure. That's what I mean. This is a group itself. So now, given any group, we've got this new thing called ought G, which is the collection of all ways to map G back onto itself. This is a group that lives above G. So, theorem, we'll do a quick proof of it. Ought G is a group do a quick proof. This is real quick proof. What is the operation?
Composition.
Composition of functions, absolutely. What is the identity in odd G? So it's the function, so it would be the function phi, let's call it like an epsilon. I don't wanna use that because it's phi e of x that gave me phi of x, no matter how I did it. So what is E? It's a function. What do you think it does? It's a function that when I compose it with other functions, it doesn't change the structure of the thing I'm composing with. What would do that? What's a function look like that doesn't change things? Let's take a stab. Just the identity function, literally. Literally just whatever passes in here comes back out. And then this is all gonna work out just like this. Does that make sense, or should I explain that? Explain a little bit? Okay. Cool. So this is the identity. It's just the identity function. E of x is just returns x. So what I mean by that is in this group, let's take phi and odd G. And is it clear that that's like one-to-one and onto? Because it just spits back out the same damn thing, the group, right? It's clear that that just gives you out your group when you pump it in. So let's take phi here. If I take phi composed with E of x, and it helps to have this little argument here. That's phi of E of x. That's just phi of x. So when I write compose with E, so this is phi kind of times E. If we're going to think of that as just like group, we know that that times means composition. I get back out phi. And then the other way is true as well. So if I took phi E, or E phi, this is literally just, this returns what's inside here, so it's just phi of x. So that means this too. So that's my identity element, the function that doesn't change anything, leaves it the same. So for any group, yeah, I mean, when you've got a group G and you want an isomorphism of G back onto itself, just send everything back to itself. That's the most trivial thing you can do. It's an isomorphism, it's an automorphism. It's very uninteresting. So I'm not I think there's some processing going on. Just wanna make sure everything's good. Kyle's contemplating that deeply. Kyle's contemplating that a little bit more. What about inverses? If I take phi in odd G, what's its inverse? say it, just try. I want to, it's what, yes? Well, so if I had multiplication, yeah, definitely. What is it with functions? I'm looking for a function that when I compose it with phi, so let me call it just I of x, I want to get the identity function back. I just want the identity, which is just x. What do you call a function that when you compose it with another function, you get back x? What do you call I, capital I here in relation to phi? You're thinking too deep. Inverse function, literally. So, given this, let's talk about this real quick. Phi inverse is literally the inverse function. Why is that in ought G? First off, why does this exist? Exists because, why? What do you need for an inverse of a function to exist? Say that again.
G is a group.
Yeah, we're not thinking about that part. We're thinking about the stuff in there. Think back more just to functions, like functionhood. So I give you a function. Here, let's talk functions. Let's review real quick. Here's a function. Looks like x squared shifted up. Does that have an inverse? Do we know how to? Is that 1-to-1? That's not 1-to-1.
No, it's not.
That's correct, yes. The other answer, yes. That's not 1-to-1. That doesn't have an inverse. What do you need for a function to have an inverse? 1-to-1, yay. And then maybe some other property that we know defines automorphism. So 1-to-1. Onto, yep. Because phi is 1-to-1 and onto. So I know that the inverse, see, it's just right there. It's just right there. I know that the inverse function exists because everything in here has an inverse by its nature of being 1-to-1 and onto. They're already isomorphisms. So that's my inverse for everything. Is this group commutative? No, I'm not stopping. Is functional composition? No, thank you.
Because if you put them in the other way, you get, okay, yeah.
You get different shit out, right? let's let's get blunt with it. So it's not a commutative group in general. We could never assume that. And the group, so I think we're good here. We've got, and then one last thing, we have to have closure. So let's take a phi and let's take an alpha and a beta in there, in ought G. Y is alpha beta, where that's composition, an element of ought G. What is that?
They're both in G.
Yeah, exactly. So they're both in ought G, so what do we know about each one of them? What does it mean to be in here? So alpha in ought G means, what does it mean? You're right, you're on the right track.
All that jazz is.
Yeah, there's a lot of jazz. What's the jazz that made that all possible? What was the definition of ought G? They're both isomorphisms, right? So that means alpha maps from G to G is an isomorphism. Let's just slow down. We got this, friends. What does it mean to be an isomorphism?
It's 1-to-1,
What?
onto, and preserves the group operation.
Oh, fuck yeah. Exactly. So right now we're not even thinking about group operations. We're just doing function stuff. So alpha is 1-to-1 and onto. Anything in here is 1-to-1 and onto. That's why it has an inverse. This is 1-to-1 and onto. I compose it with something that's 1-to-1 and onto. I one-to-one and onto. This preserves group structure. This preserves group structure. Their composition then preserves group structure. Composition of isomorphisms is still an isomorphism. So this right here implies alpha and beta are one-to-one and onto and preserve group structure. So alpha composed with beta does all those things too. Thus now we've got a group that sits above any group. I've got this little group G, and above it I've got these automorphisms. And I'm making it look bigger, it's not necessarily bigger. I got odd G, and it's the stuff that really just gets in here and moves stuff around. So, where did I want to go with that? I forgot. I don't have much longer to tell you stuff, which may be soothing to you. There's a very special kind of automorphism I want to talk about. So let's just talk about those and call it a day. And then when we come in on Wednesday, we're going to do a lot of work with automorphisms. That's going to be Wednesday's work. Kind of, we may not be meeting on Monday. That's a thing that might be a reality. We might be taking a mental health day.
I could use one of those.
Could you? You seem like you might be in need of a mental health day. I think we all are. So yeah, I think that's actually that's what we're doing.
Okay.
Mental health day Monday. Fuck that.
Sick.
It's just math. Our minds and our bodies and our happiness mean infinitely more. I might be one of the few people in the math department that believes that.
True.
So, so this group here is the collection of inner automorphisms on G equals the set of all. Okay, it's all right. It's all right. It's okay. You're gonna like it. It's not that bad. Inner automorphisms. I mean, we got Monday off, right? So we can do anything now, right? We've got like the big, like we're gonna take a nice cold shower. Right? To Kyle, that sounds probably fantastic after all
Yeah,
this.
it's pretty
you know.
normal, honestly.
You don't like them?
Oh, cold showers, I do them all the
I
time.
don't know
Yeah,
about
I
you.
started taking them too.
No, they're
I'm-
good for you.
They're good.
I
Actually,
prefer
really
to
good.
feel like I'm
Me too.
boiling.
They feel so good. They like when you're there, it's not good. Then it starts to feel better, and then you get out. You like start getting warm, right? Like get really warm.
I prefer to boil.
There's nothing wrong with that too. There's nothing wrong with feeling good. It's like a short-term suffered for a longer-term payoff, really.
You get
Inner.
used to it too.
What's that?
You get used to the cold shower too. It starts to the point where it's just normal.
Is
doesn't
it?
feel cold.
Just, yeah. Inner automorphisms on G. What does that mean? It's the collection of all automorphisms of a certain form. Phi of x is equal to ax A inverse, where A is an element of G. That's it. That's it. I thought you were shocked. You were yawning. You've gotta be kidding me. That's unbelievable. So, this is also a group itself. This is a collection of functions that is possibly a subset of, or a subgroup of aught G. So we could definitely say this, that in G is a subgroup of aught G, possibly the whole thing. So that's why I'm leaving the potential for equality in there. I'm just gonna put this up here and then maybe make it an assignment, or we'll do it on we can show, this means we're not going to, that in G is a group itself. And maybe we'll just do that on Wednesday. So we've got like 3 minutes left. Let's just take a look at the rest of the problems and make sure that I'm sending you off with enough information to complete them. So I think we did, yeah, so number 3, that should be pretty straightforward, I think, right? We gotta show it's 1-to-1 and onto R plus, show it preserves the multiplication. And then what's the next problem? We talked about 4, 5. Can you see how we might map from G to H? What could we do? It's a plausible isomorphism. Up here. Is it 3? Multiples of 3 is that?
Yeah.
Yeah. Jesus. Yeah. Thank you, sir. Any suggestions of a fee that takes us from here to here in a 1-to-1, not two-way?
Plus or minus 2, plus or minus 3.
Yeah, that's, yeah,
I
so
just
we
go straight down.
yeah, we can, let's give a, yes, beautiful. So we could literally draw some arrows here and do it, but let's get a formula, because it'll be easier to work with. What's a formula? If I want phi of 2 to equal 3, because notice here 2 is a generator, 3 is a generator, we need that to be the case. I couldn't send 2 anywhere else, except maybe to -3, that could work. But like what, here's the next one. So this would mean that 2 plus 2, 4, had to get to 3 plus 3, 6, so we need that. Can we think of a function here? I think that sounds like a beauty. Cool. And that's going to be well defined because everything in the first group is even. So when you divide by 2, everything's kosher. When you multiply by 3, you get something in the next group. So I would use this as my function for that problem. Is that the last problem then, too?
So I got 7.
Oh, what was 7 and 8?
Alright,
Okay.
7 is just give 3 reasons why S4 is not isomorphic to D12.
So look at element orders, group size. Well, group size isn't going to help you. They're the same size, but. That one is going to be looking at element orders, and then number 8 was also.
Yeah.
Are we going to be? Do we know log properties? Yeah. Do we know that log of a x y is log of x plus log of y? And if we didn't, maybe we should write it down to remind ourselves, because I think that'll be your friend right there for that one.
X times Y and Y.
That is x times y, yes, ma'am. Cool. Yeah, I figured. That's why I thought maybe just touch upon it. Yeah, I like this. I'm gonna start doing this mental health break between fall break and Thanksgiving break. It's a long stretch. Recommended by a neuroscientist, so we have to do it, I think. You don't have to talk about this in your other math classes, by the way. You don't have to mention.
I don't know, I'm pretty convinced know, we're all really feeling the stress of the school year. I really just think we
Definitely
should-
don't tell that.
Thank you.
Okay.
Where's my other?
Now I gotta remove that part of the video. Quick little edit.